Good afternoon, class.
Good afternoon, sir.
I'm here to continue our last topic, which is what energetics. I think in our last topic, we treated entropy. And I said entropy is total what heat content of what of a system. And from our last class, I said entropy, which is the total heat what content of a system. We also have the fraction of that what total what heat content, which does what useful work. Which does what useful work is known as what gives free energy. Yes or no? I mean gives free energy. Why the part which is related to the disorderliness of the system is known as what? Entropy of a system. So now in this class, I'm going to talk about what entropy. What is the meaning of what entropy? Entropy is the degree of disorderliness or randomness of what of a system. The degree of what randomness or what disorderliness of what of a system. Now entropy is also what a state function, which is calculated mathematically as what delta S standard, which is equal to what summation of heat of what entropy of products minus summation of heat, that means entropy of what reactants. Since it's a what state what product. But we also have something called what entropic what factor. But as a chemist, change in entropy is more important than what entropic what factor. Our entropic factor is giving us what Q equals to what? Change in what? Entropy over what? T. If you what cross multiply from here, you're going to have what delta X raised power what? Theta equals to what? So we're going to have our what delta X raised power what? Theta equals what? Q over what? T. Making Q the subject of the formula, which is what our entropic factor, T equals what delta S raised power what? T. So note what this formula. Now, this is known as what? Entropic factor. There are factors that what determine the entropic factor of what of a system, which are two in number. The first one is what? Temperature. The two is nature of the substance. The nature of what? Of substance. Now, how does what temperature affect the entropic of what? Of a system? Increase in entropy is going to lead to increase in entropy of what? Of a system. Since if there is what? Increase in what? Temperature, the particles of a system, they're going to what? Acquire energy, which is going to lead to increase in the rate of the disorderliness, which simply means what? Increase in entropy is going to lead to what? Increase in what? An entropy of what? The system. Do you get it? Now, let me now what? Tell you something about what? Entropic and temperature. All what substance does not have what? A zero what? Entropy. Even though at 0 what? Degrees Celsius. Only a solid what? Crystalline what? Substance have what? 0 degree, have 0 entropy. At absolute temperature. What's the meaning of absolute what? Temperature? That is what? 0 what? Kelvin or minus 273 what? Degree what? Celsius. Only a solid what? Crystalline what? Substance have what? 0 entropy at what? Absolute what? Temperature. Now, if you want to know about what? Entropy and what? Temperature. Just look around here. This building that we are now does what? Vibrate, even though at what? This 0 what? Degree Celsius. At the 0 what? Degree Celsius, this building is still in vibration. That means the particle are not having 0 what? Entropy at what? 0 what? Degree Celsius. That's the meaning. Now the next one, nature of what? The substance. As we move from solid to liquid and to what? Gas, the entropy of the system what? Increase. What do I mean? As the system, that means as the nature of the system decreases, that means there is increase in what? Entropy. Because the molecular force of attraction holding the what? The particles get what decreases. As that's what first what get decreases, the entropy of the system what increases. What do I mean? From solid to liquid to what to gas, there is what increase. Increase in what? Entropy of that what? Of that system. Now, if you want to know the comprehensive what meaning of entropy, it is being stated in second law of thermodynamics, which says increase in entropy. Thus, as a result or the need of a greater disorderliness of a system which does what? Changes. A comprehensive what? Meaning of entropy is being given in second law of what? Thermodynamics, which says what? Increase in entropy. Thus, a need for a greater disorderliness of the system is a factor or a result of what? Change of that what? System. We have so many examples which what we can use. That means the flowing of what? Of a river. The conversion of what? Liquid water to what? To gaseous what? Water. And so on. Now, if our entropy delta X is given in positive, that means there is increase in entropy of that what? System. That means increase in what? Entropy. If our delta X is equals to what? Negative, that means there is decrease in entropy of what? Of the system. If our delta S equals to 0, we have there is no change. No change in entropy of what? Of the system. Now let me make use of these two examples. Now look at what this system. We have PCl5 to give PCl3 plus what? Cl2. We also have ammonia, Haber process, which we have what? Hydrogen reacting with nitrogen gas to form ammonia. And the last one, which is HR, which is going to give us what? Hi2 plus what? I2. Gas, gas, gas. We are having what? 2 air. They are all what? Gas. Now the first one, if they ask you to predict the change in entropy of what? This system, is it going to be an increase in entropy or a decrease in what? Entropy? Look at what this system, the number of what? Mole of the initial what? Initial what? State is lower or smaller than the what? Number of mole of what? The final what? State. Here we are having 1 mole of a gas with what? 1 mole of a gas. Therefore, there is going to be what? An increase in entropy because the number of mole of what? Product we are having is greater than the number of mole of what? The reactant we are having. Now look at what the second one. Therefore, in the first one, our delta X is going to give us what? Positive. Now the next one, whereby we are having 3 mole of what? Hydrogen gas reacting with what? 1 mole of what? Nitrogen gas to give what? Ammonia. The number of mole of our what? Reactant what? Gaseous species are more than the what? Number of mole of what? Our product what? Gaseous what? Species. Therefore, there is going to be what? A decrease in the entropy of that what? System. Because the number of mole of what? The gaseous species in our initial state is higher than the what? Number of mole of the what? Gaseous species in the what? In the product state. Now look at this last one. We are having what? Gaseous species, gaseous species, gaseous species. We are having what? 2 mole of what? Gaseous species in the initial state. At the final state, we are also having what? 1 plus 1, which is what? 2. There are what? Equal what? Number of mole. Therefore, our what? Change in entropy here equals what? 0. There won't be change in what? In the entropy of that what? Of that system. Do you understand now? Now let us quickly talk about what gives free what? Energy. Gives free energy is the energy that is useful to a system or that does what? Usefulness to a system. What is the meaning of what this gives energy? It is popularly used to determine the spontaneity of what? Of a system. If a system is going to be what? Probable. What do I mean? Probable. or the system is going to be what? Visible. We can use the value of what gives free energy to determine that. Now, what is the meaning of what gives free energy? I said it's the energy that does what? Useful work towards a system. Look at what this what probable or what improbable. At a certain what temperature, a system is going to have a certain what gives free energy. That gives free energy at that certain temperature is going to determine if the system is going to proceed, that means going to what? Function, or is going to happen. Now, this is what I mean. Look at this. If we have our delta G to be what? Negative at a particular temperature. Let me just say at any temperature. So that means the system is going to be visible at any what? Temperature. Do you understand what I'm saying? If our delta G is positive, it means the system at any temperature, it means the system, it will not be what? Probable. That means improbable what? System. And if our delta G is equal to what? 0 at any what? Temperature, that means the system is at what? Equilibrium. Now, in gives free energy, there is what? Two terms. The first one is what? Maximization of potential energy. And the second one is the what? Maximization of entropy factor. Now look at this. These are formula do using what gives free energy, which is what? Delta G equals to what? Delta A standard minus what? T delta what? S. Let me tell you how we get it. I said our entropy is the total heat content of what? Of a system, yes or no? That means delta what? A standard equals to the fraction that does what? Useful work is known as what? Gives free energy, yes or no? The other fraction is known as what? Entropy, which is used for what? The randomness or what? Disorderliness of the system, which is what? Q. Are you with me? Now, don't forget that our Q equals what? T delta what? S standard. Now, let us replace our Q with that. We're having what? Delta H to give us what? Delta what? G standard plus what? T delta what? S standard. So, my delta G standard will now give me what? Delta H standard minus what? T delta what? S standard. So, with this, we can solve any question under what? Free gives energy. A reaction of nitrogen 2 oxide. In a reaction to produce what? Nitrogen 2 oxide. If the entropy of the what? Reaction is plus 90 what? Kilojoule per mole. And the entropy of the system is 12.0 joule per mole per Kelvin at 25 degree what? Celsius. Determine the Gibbs free energy of the system. Determine the Gibbs free energy of what? Of the system. Now, what is our formula? We have what? Delta G standard equals what? Delta H minus what? T delta what? X. So, our delta G equals to what? What is our delta what? H given to us? It is what? Plus what? 90 what? Kilojoule what? Per mole. What is my T? Now, here we're going to convert our temperature into what? Kelvin. We can use what? Degree Celsius. So, add what? Plus 273. What do I have? That is 298 Kelvin. Now, look at this. We are having kilojoule per mole. But our Gibbs free energy is measured in kilojoule per mole. But our entropy here is given as what? Joule per mole per what? Per Kelvin. So we need to convert this into what? Kilojoule first before what? Using it. Take note of that. So 12.0 divided by what? 1000. What do I have? That's 0.01 what? 2 kilojoule per mole per what? Kelvin. So let me what? Put in my value. So I have what? 29.8 Kelvin times what? 0.012 Kelvin kilojoule per mole per what? Per Kelvin. Now look here, I'm having Kelvin here. Kelvin is going to cancel what? Per Kelvin. I'm going to be left with what? Kilojoule what? Per mole. So let me to do it. plus 90 kilojoule per mole minus what? 86 point what? 4. That is kilojoule per mole. 3 point what? 5 what? 6 kilojoule what? Per mole. So what is the final answer? 86 point what? 4 kilojoule per mole. Now, they can ask you to comment on your what? On your answer. Since our data what G is equals to what? 86 point what? 4 kilojoule per mole. That means the reaction will not be what? Visible at this what? Particular what? Temperature. For us to make what? This reaction what? Visible or what? Spontaneous, we are going to increase what? The temperature we are working what? In. Are you with me? If this what? Temperature is high enough, if the value here is what? High, therefore our value here will be what? Low as compared to what? To this value. So our delta G is going to give us what? Negative value. Are you there? So thank you for what? For listening.